Welcome to this video. Today, we'll be diving into the problem titled Sum Root to Leaf Numbers. This is a fascinating problem that requires navigating a binary tree to calculate the sum of numbers represented by root to leaf paths. Stay tuned as we explore the intuition, approach, and implementation to solve this problem step by step. In this problem, we are working with a binary tree, and the goal is to find the total sum of all root to leaf numbers. Let's break this down. A root to leaf path represents a number, where each node along the path contributes one digit to the number, starting from the root. For example, if a path in the tree is from a root node with value 1 to a leaf node with value 3, passing through a node with value 2, the number formed is 123. The task is to compute the sum of all such numbers for all root to leaf paths in the tree. A node is considered a leaf if it has no children. The input to the problem is the root of a binary tree, where each node contains a single digit between 0 and 9. The output should be an integer representing the total sum of all the numbers formed by these root to leaf paths. Now, let's look at a couple of examples to understand this better. In the first example, the binary tree has a root node with value 1 and 2 child nodes, 2 on the left and 3 on the right. The root to leaf paths here are 1 to 2, forming the number 12, and 1 to 3, forming the number 13. Adding these together gives 12 plus 13, which equals 25. In the second example, the tree is slightly larger. The root node is 4, with children 9 and 0. The node with value 9 has two further children, 5 and 1. The root to leaf numbers formed in this case are 495, 491, and 40. Summing these gives 495 plus 491 plus 40, which equals 1026. These examples illustrate how to calculate the total sum of all root to leaf numbers in different tree structures. There are a few constraints and edge cases we need to consider for this problem. First, the number of nodes in the tree can range from 1 to 1000, so the solution needs to handle trees of varying sizes efficiently. Each node's value is an integer between 0 and 9, which simplifies the number formation process but requires careful handling during traversal. The tree node is defined using a simple class structure, where each node has a value and pointers to its left and right children. As for edge cases, if the tree consists of only a single root node, the result is simply the value of that node. If all nodes in the tree have the same value, the solution must ensure that paths are still interpreted correctly as unique numbers. Finally, for very large trees with the maximum constraint of 1000 nodes, it's important to ensure that the solution is efficient and avoids unnecessary computations. To solve the problem of summing all root to leaf numbers in a binary tree, one possible approach is the brute force method. Here's the intuition: you generate all possible paths from the root to each leaf node, converting each path into a number by combining the node values along the way, and then summing these numbers. This can be achieved using either a depth-first search or breadth-first search. As you traverse the tree, you'll construct the number represented by each path, and at every leaf node, add this number to the total sum. However, this approach has some drawbacks. The time complexity can be as high as n squared, because for each path, we perform additional work proportional to the height of the tree. The space complexity is h, where h is the tree's height, due to the recursion stack. While this method is intuitive, it involves redundant computations when reconstructing path numbers repeatedly, which makes it less efficient for larger trees. Now, a more efficient solution is to optimize the process using recursive DFS with number construction. Instead of explicitly storing and reconstructing paths, we maintain a running sum that evolves as we traverse the tree. As we move down each level, we multiply the current sum by 10 and add the value of the current node. When we reach a leaf node, the running sum directly represents the number for that path, which we then add to our total sum. This approach minimizes overhead because we calculate the path number incrementally, without storing extra data. The steps are straightforward: start at the root with a running sum of 0, recursively compute the new sum at each node, and add it to the total when you encounter a leaf. The time complexity here is n, as we visit each node exactly once, and the space complexity remains h, due to the recursion stack, where h is the tree height. This method is both elegant and efficient, addressing the inefficiencies of the brute force approach. This optimized approach is significantly more efficient because it avoids redundant computations by directly updating the running sum during traversal. It also leads to a cleaner and more concise implementation. Based on these benefits, we have chosen recursive DFS with number construction as the strategy for solving this problem. There are several reasons for this choice. First, it is efficient, with optimal time and space complexities that make it suitable for handling large trees. Second, it is simple to implement, which reduces the likelihood of errors. Finally, it avoids the overhead of explicitly storing and reconstructing paths, focusing instead on incremental arithmetic operations. One of the key insights here is that each root-to-leaf path represents a unique number, and constructing this number incrementally by multiplying the running sum by 10 at each step is both faster and more elegant. This approach not only mimics the way numbers are built digit by digit but also eliminates unnecessary work. When comparing the brute force method to the optimized recursive DFS, the differences are clear. While the brute force approach is easy to conceptualize, it becomes impractical for larger trees due to its inefficiency. In contrast, the optimized method strikes a balance between simplicity and performance, making it far more suitable for this problem. Additionally, though an iterative DFS could reduce space complexity slightly by avoiding recursion, it involves more bookkeeping and complexity in the implementation. The recursive approach, on the other hand, naturally aligns with the structure of the tree and results in cleaner, more intuitive code. In summary, the recursive DFS with number construction is the ideal choice for solving this problem, offering a combination of efficiency, simplicity, and scalability that makes it stand out as the best solution. To solve the problem of summing all root-to-leaf numbers in a binary tree, we need to start by understanding the structure of the problem. Each path from the root of the tree to a leaf node forms a number by concatenating the digits along that path. For instance, in a binary tree with nodes 1, 2, and 3, we have two root-to-leaf paths. 1 to 2 forms the number 12, and 1 to 3 forms the number 13. The goal is to find the sum of all such numbers, in this case, 12 plus 13 equals 25. The most efficient way to achieve this is by traversing the tree using depth-first search, or DFS. During the traversal, we'll keep track of a running number that represents the current path's value. When we reach a leaf node, we'll add that number to the total sum. To break this down, we start at the root of the tree with an initial total sum of 0 and proceed to traverse the tree while maintaining the running number for each path. The algorithm proceeds with a DFS traversal to calculate the sum of the numbers. Starting at the root, we pass the current node and the running number, initialized to 0, into the DFS function. At each node, we update the running number by multiplying it by 10 and adding the node's value. For example, if the running number is 12 and the current node's value is 3, the updated number becomes 123. If the current node is a leaf, meaning it has no left or right child, we add this running number to the total sum since it represents a complete root-to-leaf number. Otherwise, we recursively visit the left and right child nodes, if they exist, continuing to build the running number as we go. Once the entire DFS traversal is complete, the total sum will hold the result. We also need to consider termination conditions and edge cases. If the tree is empty, the function should return 0. If there's only one node, the result should simply be the value of that node. Unbalanced trees, where some nodes only have one child, are naturally handled by the DFS process. To implement this algorithm, we rely on the binary tree structure and the recursive DFS approach. The binary tree serves as the input, where each node has a value and pointers to its left and right children. The recursion stack acts as an implicit data structure that allows us to explore one path fully before moving on to the next. Let's consider an example to see this in action. Imagine a binary tree where the root node is 1, with children 2 and 3. Node 2 has two children, 4 and 5, while node 3 is a leaf. Starting at the root, the running number is initialized to 0. For node 1, we update the running number to 1. Moving to the left child, node 2, the running number becomes 12. At node 4, which is a leaf, we compute the running number as 124 and add it to the total sum. Similarly, for node 5, another leaf, the running number becomes 125, which is also added to the total sum. After completing the left subtree, we traverse the right subtree starting from node 3. Here, since node 3 is a leaf, the running number is updated to 13 and added to the total sum. At this point, we've visited all root to leaf paths, and the total sum is 124 plus 125 plus 13, which equals 262. Translating this logic into code, we use a recursive DFS function. The function takes the current node and the running number as parameters. If the current node is null, it returns 0. Otherwise, we update the running number using the formula, current number times 10 plus the node's value. If the node is a leaf, we return the running number. If not, we recursively call the function for the left and right children and sum their results. The final result is obtained by calling this DFS helper function starting from the root with an initial running number of 0. Analyzing the performance of this algorithm, the time complexity is O(n), where n represents the number of nodes in the tree. This is because each node is visited exactly once. The space complexity depends on the height of the tree, as the recursion stack holds at most one path at a time. In the worst case, for an unbalanced tree, the height could be equal to the number of nodes, making the space complexity O(n). In a balanced tree, the height is proportional to the logarithm of the number of nodes, resulting in a space complexity of O log n. To optimize further, we can avoid recalculating the running number for each path by maintaining it during traversal. Additionally, while our implementation uses recursive DFS, an iterative approach with an explicit stack could provide better control in scenarios with very deep trees. Finally, edge cases such as an empty tree or a skewed tree are naturally handled by the algorithm since it processes all nodes in a consistent manner, regardless of the tree's structure. This Python implementation solves LeetCode problem number 129, sum root to leaf numbers, using a recursive depth-first search (DFS) approach. The SumNumbers function accepts the root of a binary tree as input. It defines a helper function DFS to traverse the tree recursively. The DFS function takes two arguments, the current node and the cumulative sum of numbers formed from the root to the current node. Initially, the function is invoked with the root node in a current_sum of 0. If the node is none, i.e., the base case for recursion, it returns 0 since no number is formed from an empty path. For each node, the current_sum is updated by multiplying the existing sum by 10 and adding the node's value. This operation ensures that the path's digits are concatenated correctly. If the current node is a leaf, i.e., it has no left or right children, the function returns the current_sum, as this represents a complete root to leaf number. For non-leaf nodes, the function recursively computes the sums for the left and right subtrees, passing the updated current_sum down the recursive calls. The results of the left and right subtree calculations are added together and returned, ensuring that all root to leaf numbers are included in the final sum. The SumNumbers function returns the result of the DFS call on the root node, providing the total sum of all root to leaf numbers in the tree. This approach efficiently traverses the tree in O(n) time, where n is the number of nodes, as each node is visited exactly once. Here, we define the SumNumbers method, which serves as the entry point for our solution. It takes the root of the binary tree as input and initiates a depth-first search by calling the DFS helper method. The DFS method is where the main logic resides. It takes two arguments, the current node and the cumulative sum calculated so far. If the current node is null, we simply return 0 because there's no contribution to the total sum. Next, we update the current sum by appending the current node's value. This is done by multiplying the existing sum by 10 and adding the node's value, effectively constructing the number as we traverse the tree. If we reach a leaf node, identified by both left and right children being null, we return the current sum since this represents a complete root to leaf number. Otherwise, we recursively calculate the sums for the left and right subtrees and return their combined total. This ensures that all root to leaf paths are accounted for in the final result. Finally, we define the treenode class, which represents the structure of each node in the binary tree. Each node contains an integer value, val, as well as references to its left and right children, which are also treenode objects. The constructor initializes the node with a specific value and sets the child references to null by default. This class is essential for representing the tree structure used in the SumNumbers method. With this, our implementation is complete, and the depth-first search approach ensures we traverse the entire tree to calculate the sum of all root to leaf numbers efficiently. To solve this problem, we start by examining a simple binary tree. The root node is 1, and it has two children, 2 and 3. Initially, the current underscore sum is set to 0. At the root node, we update the current underscore sum by multiplying it by 10 and adding the value of the current node. This gives us current underscore sum equals 0 asterisk 10 plus 1 equals 1. From here, we move to the left child, node 2. At this point, current underscore sum is carried forward as 1. Again, we update it, current underscore sum is equal to 1 times 10 plus 2 equals 12. Since node 2 is a leaf node, we return 12. Next, we go back to the root node and move to the right child, node 3, where current underscore sum is still 1. We update it similarly, current underscore sum is equal to 1 times 10 plus 3 equals 13. As node 3 is also a leaf node, we return 13. Finally, we combine the results from the left and right subtrees by summing them up, 12 plus 13 equals 25. So, the final output for this tree is 25. Now, let's consider a slightly larger tree. The root node is 4, with children 9 and 0. We start with current underscore sum equals 0 and update it at the root, current underscore sum equals 0 asterisk 10 plus 4 equals 4. Moving to the left child, node 9, we carry forward the current underscore sum as 4 and update it, current underscore sum is equal to 4 times 10 plus 9 equals 49. Continuing further down the left subtree, we reach node 5, and the current underscore sum becomes 49 asterisk 10 plus 5 equals 495. Since node 5 is a leaf, we return 495. Next, we go back up to node 9 and explore its right child, node 1, where the current underscore sum is again 49. At node 1, we update the current underscore sum as current underscore sum is equal to 49 times 10 plus 1 equals 491. Since node 1 is a leaf, we return 491. Now, we combine the results from the left and right subtrees of node 9, 495 plus 491 equals 986. Returning to the root node, we proceed to the right child, node 0. Here, the current underscore sum is 4. We update it to current underscore sum is equal to 4 times 10 plus 0 equals 40. As node 0 is a leaf, we return 40. Finally, we combine the sums from the left and right subtrees of node 4, 986 plus 40 equals 1026. This gives us a final output of 1026 for this tree. Additionally, consider the case of a single node tree where the root is 7. In this case, we start at the root node, which is also a leaf. The current underscore sum is initialized to 0 and updated as current underscore sum equals 0 asterisk 10 plus 7 equals 7. Since the node is a leaf, we return 7 as the final output. This example highlights some key insights about the problem. The current underscore sum is updated at each step by multiplying the previous sum by 10 and adding the current node's value. Leaf nodes act as the base case for recursion, returning the accumulated sum for their path. The final result is obtained by summing all root-to-leaf path numbers. The depth-first search approach ensures that all paths are explored efficiently, and empty subtrees return 0. This method is both elegant and efficient, with a time complexity of O(n), where n is the number of nodes in the tree. The time complexity of this algorithm is O(n), where n represents the total number of nodes in the binary tree. This is because the function employs a depth-first search, or DFS, to traverse the tree, visiting each node exactly once. For every node, a constant amount of computation is performed. Specifically, the algorithm updates the current sum using the formula current underscore sum equals current underscore sum asterisk 10 plus node dot val and then makes recursive calls to the left and right child nodes. Since no node is revisited, the total work is directly proportional to the number of nodes, leading to a time complexity of O(n). In the best case, where the tree is empty, the function terminates immediately with O(1) time. For a balanced tree, all nodes are visited once, keeping the complexity at O(n). Even in the worst case, like a completely skewed tree where all nodes are along a single path, each node is still only visited once, so the complexity remains O(n). The space complexity of this algorithm is O(h), where h represents the height of the binary tree. This is because the maximum depth of the recursion stack corresponds to the tree's height. In the worst-case scenario, such as a completely skewed tree, the height of the tree equals the total number of nodes, making the space complexity O(n). However, in the best-case scenario, where the tree is perfectly balanced, the height of the tree is logarithmic with respect to the number of nodes, resulting in a space complexity of O log n. The memory usage can be broken down into two main components. First, the recursive stack consumes memory proportional to the height of the tree. Second, the current underscore some variable, passed as an argument in each recursive call, does not use additional memory beyond its scope. Since no auxiliary data structures like arrays or queues are used, the overall space usage is minimized. Comparing this approach to a naive solution highlights its efficiency. A brute force method might generate all root-to-leaf paths explicitly, storing them as strings or arrays, then converting these paths into integers to compute the sum. This would require O, n asterisk k, time and space, where k is the average length of each path. In contrast, the DFS approach used in this solution avoids storing full paths, reducing both time and space complexity to O, n, and O, h, respectively. Mathematically, the time complexity remains O, n, because each node is visited once, and every visit involves constant time operations. The space complexity is determined by the recursion depth, which depends on the tree's height. For a balanced tree, the height is O log n, and for a skewed tree, it is O, n. This makes the space complexity O, h. Overall, this algorithm achieves optimal performance in both time and space for solving the problem. When solving this problem, there are a few common mistakes to watch out for. First, failing to handle edge cases like an empty tree can result in runtime errors. Always check for a null root and return the appropriate base case, such as 0. Another frequent issue is miscalculating paths. It's important to construct numbers from root-to-leaf paths by updating the path value as current underscore path asterisk 10 plus node underscore value at each step, rather than simply summing node values. Additionally, using strings to build path values can introduce inefficiencies and potential errors, like forgetting to convert back to integers when summing. Numeric operations are more reliable and efficient here. Finally, if you're using global variables or shared state in a recursive approach, not resetting those values after processing a path can lead to incorrect results. Instead, pass state as parameters in your recursive calls to keep everything clean and isolated. Another potential pitfall arises when you ignore the possibility of negative or non-standard node values, such as values outside the range of 0 to 9. Always read the problem constraints carefully to avoid incorrect assumptions. From an interview perspective, this problem is a great way to demonstrate your understanding of recursion fundamentals. Be prepared to clearly explain your base case and recursive case, as interviewers are often looking for clarity in your thought process. Efficiency is another area to focus on. While brute force solutions might work for smaller trees, discussing optimizations like avoiding redundant calculations shows depth in your problem-solving skills. Additionally, for very deep trees, keep an eye out for integer overflow. While Python handles large integers gracefully, in other languages, you may need to use modular arithmetic or similar techniques. Finally, prepare for variations of this problem, such as counting root-to-leaf paths that meet certain conditions, summing paths with specific constraints, or generalizing the solution to non-binary trees. To build a deeper understanding of this problem, it's helpful to explore related problems. For instance, LeetCode 112, PathSum, and LeetCode 113, PathSum 2, both involve traversing trees to calculate specific sums, while LeetCode 257, Binary Tree Paths, focuses on constructing all root-to-leaf paths. These problems share similar concepts and will give you a broader perspective on tree traversal techniques. When it comes to solving some root-to-leaf numbers specifically, there are several approaches you can take. Using depth-first search recursively is often the simplest and most intuitive method, but it does rely on the call stack, which could lead to stack overflow for very deep trees. Alternatively, iterative DFS avoids recursion-related issues by using an explicit stack, though managing this stack can be error-prone. Breadth-first search is another option. It processes nodes level by level and can be particularly useful for variations of the problem, but it tends to consume more memory because of the queue required to store nodes. Finally, there's the Morris traversal approach, which is an advanced technique that uses O1 space for traversal by temporarily modifying the tree structure. While this method is space efficient, it can be tricky to implement and unnecessary unless specifically required by the problem. For most scenarios, the other methods we've discussed, recursive or iterative DFS and BFS, are more straightforward and sufficient. Morris traversal is worth exploring if you're looking to expand your toolkit, but it's important to weigh its complexity against its benefits for this particular problem. Great job making it to the end. Let's quickly recap what we covered. We solved the sum root to leaf numbers problem, focusing on traversing binary trees and calculating sums. Remember, mastering recursion is key to solving such problems efficiently. If you enjoyed this video, please like, share, and subscribe to stay updated with more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!